So there is one more bifurcation, and then we will have completed the whole zoo of bifurcations that only involve equilibrium points. We will have covered all of them. And it's a kind of bifurcation that occurs, for example, in the equation for the Alley effect. Now let's remind ourselves, first of all, what these terms mean. This is the birth term. That's a birth rate. We chose the value 0.1 as the per capita birth rate. This is the carrying capacity, or the crowding factor, where, of course, K is the carrying capacity. And x over a minus 1 is this threshold effect of the minimum size that you need to be viable, right? If x is less than that minimum size, then this is less than 1, minus 1 is negative. It means you're going to go back to 0. Whereas if x is bigger than a, then that's positive, and it means you're going to grow. So if we look at this in state space, a is the threshold, k is the carrying capacity, and then if we examine the stability of the equilibrium points, which we did previously, you see that if it's less than a, the vector field is negative, because this is always positive. That term is always positive. If x is less than a, this term is negative, and this term is positive. So we got positive, positive, negative. That's negative. If x is bigger than a, this is positive. This is positive because it's less than k, and that's always positive. So the vector field there is positive. And then when x is bigger than k, x over k is bigger than 1. This term becomes negative, and we have a stable equilibrium point. So a is unstable, 0 is stable, k is stable. And that's the Alley effect. Now what I want to do is I want to look at the effect of changing a. So now a is going to become a parameter, and I want to move it around. In particular, we had assumed here always that a is less than k. But now I want to consider the case in which a is actually bigger than k. In other words, the minimum cohort size necessary to grow, which is a, is actually bigger than the carrying capacity of the environment. So what happens when a is bigger than k? Well, now the situation changes. Let's make our bifurcation diagram, or rather, let's make our state space. Here is k, and here is a. A is now bigger than k, and here is 0 as always. And now the question is, what's the vector field? And the answer is, if x is less than k, and also less than a, x is less than a, this is less than 1. So this term becomes negative. X is less than k, so this term is less than 1. 1 minus it is positive. This is positive, positive, negative, which means that for x less than a, the vector field is negative. So if x is less than k, and therefore also less than a, x is less than k means that this is less than 1, so this is positive. this is always positive. And if x is less than a, this is less than 1 minus 1, that's negative. That's positive, positive, negative. That's negative. Conversely, if x is between k and a, then x is bigger than k, so this becomes negative. This is still negative. Now we have positive, negative, negative, so this becomes positive. And then if x is bigger than a, this is positive, this is negative, this is positive, and we have a negative. So now we have a funny situation. The carrying capacity is now unstable because it's less than the minimum size necessary to survive, the minimum size in terms of numbers necessary to survive. So now we have a positive equilibrium and, a stable equilibrium and an unstable equilibrium, and this is, as always, a stable equilibrium at 0. So now we want to make a bifurcation diagram. So these are the two situations for the LE effect, and one, as we're varying this parameter a, if a is less than k, we have a stable equilibrium at k and the unstable threshold at a. If a is bigger than k, k is no longer a stable equilibrium. And the only stable equilibrium is going to be at a, which is unfortunately larger than the carrying capacity of the environment, so that's not going to happen. So it's bad news for that species because the minimum population size for survival is bigger than the carrying capacity of the environment. In other words, you need a bigger population than the environment can support. So you are not going to do well. But now let's notice an interesting thing about the bifurcation that just occurred. And then we'll draw the bifurcation diagram. But just an observation about the bifurcation. We define a bifurcation as a change in the number or stability of equilibrium points. And now we look at this and we say, well, how many equilibrium points did we have when a was less than k? Well, we had 1, 2, 3. How many equilibrium points do we have when a is bigger than k? Well, we have 1, 2, 3. So we haven't gained or lost equilibrium points, but they have changed their stability. So let's make the bifurcation diagram. We're going to put the parameter a on that axis. And as always, on the y-axis, we're going to put the state space x. So no matter what the value of a is, we will always have a stable equilibrium at 0. And that's just going to be there forever. So that's a stable equilibrium. Now, let's follow what happens as a increases. So for a, and of course, we have to put the all-important value k right there. Now, as a increases, I'm just going to give myself a little dotted line here. As a increases, you see that the location of the equilibrium point, of the unstable equilibrium point at a, gets larger and larger. And I'm going to use pink here for unstable. And this is just going to increase linearly with a. until that point. Now, what about the equilibrium point at k, which is right there, x equals k? Well, that was always stable, 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 until a got bigger than k. When a got bigger than k, the a equilibrium becomes stable, and the k equilibrium becomes unstable. So now we have a new kind of bifurcation diagram where this was always stable and doesn't change, but the two equilibrium points, x equals k and x equals a here, at the point a equals k, they just exchange their stability. A had been unstable, it's now stable. K had been stable, it's now unstable. So this is a new kind of bifurcation. It's called transcritical bifurcation. And with saddle node bifurcation, pitchfork bifurcation, transcritical bifurcation, we have now covered all the bifurcations that can occur that involve only equilibrium points.